So now I think it's the most juicy part of the podcast, at least for me personally. We are approaching to the design process behind the SenseGlove. And I understand there might be some proprietary information, but as much as you can, please maybe share with us what made the present SenseGlove a SenseGlove. Basically, feel free to mention anything about the design process behind it, how you guys started, maybe prior research that inspired you in terms of the design process, right? Any user studies you run in the beginning. Also, please mention any mistakes maybe you made on the way and how you learned from them, or any challenges, things like that.
Oh, sure. Yeah. So maybe good to start with our kind of design assignment that we had. And that was fully focused on virtual reality training. So we wanted to create an haptic wearable that was ideally suited for the implementation of virtual reality trainings in manufacturing environments, but also in healthcare environments. And what you see, if you want to train someone, the interaction with the particular physical objects that you have need to, well, digital physical objects in a sense, they need to be as realistic as possible, because that's if you it's kind of how you build your muscle memory in a sense. If I pick something up from a certain height of a shelf with the same grip, and I connect like a cable next into it, I really want to have that same motion as I would do in real life, also replicated in the virtual environment. So that was our assignment, to create a tool for that. And then obviously all the boundaries, so it should weigh less than 300 grams. It should work wirelessly. It should work with standalone VR headsets. It should work with, it should have a certain price point. So it is not something that is, where companies cannot afford it to have it into their virtual reality trainings. So we had, the end customer end price should be below 5,000 euros if you have, if you sell one unit in a sense. So that was kind of what our design assignment was. And then looking back at what we already done with our DK1, we've built like an exoskeleton wearable, and we got a lot of feedback from, hey, yeah, it's an exoskeleton is nice from like a mechanical point of view, but it is scary. I feel Edward Scissorhands with a blue big exoskeleton on my hands. So I really wanted to also go for a design, look, and feel that was less scary, and just really represented the glove rather than an exoskeleton in a sense.
Right.
So that was how we shifted, like from the exoskeleton to the Nova product in the appearance in a sense. And to come back to the haptics, our core technology lays firstly around magnetic friction brake technology for creating force feedback that allows us to have quite some strong force feedback, like 20 Newton, 2 kilograms on each finger, with like limited power consumption, with very like rapid speeding up of that mechanical friction brakes. So we took that technology out of the DK1 and embedded that into the Nova as well. So that was quite easy to say, okay, that is the way how we also gonna perceive the force feedback inside the new device. But what was interesting inside there is that we wanted to obviously save weight and energy consumption. So
that was another question I wanted to ask about.
We cut it out of the pinky of the force feedback. So there's no force feedback on the pink, and there's also no motion capturing sensor on the pinky. And we actually did that with a very quite elaborative study. We did a lot of business fairs with our DK1, and on 2 fairs, namely the CES from 2090 or something, and one of the Laval events prior to COVID. We just did not give anyone who was trying our product, our DK1 product, force feedback and motion capture on the pinky. We just related it to the ring finger. And out of the around 200 participants, only 2 noticed that there was no force feedback on the pinky. So that was quite a elaborate user study where we found, okay, well, we don't need a pinky. It saves us like 50 grams because we don't need that particular motor, and it saves
Who needs the pinky?
quite some energy consumption.
Exactly.
So,
no, it's great. I mean, this is great.
that might be a nice, interesting design insight. And we often get that question, like, why don't you have that pink? Why don't we have force feedback on the pink? And then, okay, yeah, this is the reason for it.
Well, it's important rationale.
Yeah. And then we really wanted to design for the interactions that were mostly used in training. So a lot of our clients use our glove in like manufacturing environments and manufacturing training, where you have a lot of buttons. So we wanted to have, you click obviously buttons with your index finger and sometimes with your thumb as well. So we want to have a vibrotactile actuator on those fingers in order to resemble those interactions nicely.
So you would go in the field and observe the interactions of your users, your kind of primary users, right?
Yeah. And then we kind of mapped over 100 different type of interactions that were important to our clients. And we kind of assembled the haptic feedback ranges of what we actually wanted to have. And also, a lot of power tools were used, and also a lot of, second order haptics were used. So where you would have a tool inside your hand and like hammer on something. So that's also the reason why we chose in the palm of the hand, or like at the back of the hand, a very low or wideband actuator that had a very low frequency range in order to resemble things like drills that you have inside your hand that kind of vibrate at around 60 hertz vibration rate. And also when you have impact stimulation, you want to have like a high force of vibration resembling, hey, I'm really hitting into something.
Okay, this is already my next other question actually also, but let's then combine it actually, because you already mentioned about some design constraints, right, that you had initially, that you took into consideration when you developed your exoskeleton initially, right, and then you moved into other form factor, considering that you wanted to make it more user-friendly and less scary, right, for future users. Also cost was of course a consideration. Then you talked about observing your users, right? The interactions that they need, right? So you addressed that in specific, in terms of a specific body location, right? Fingers location in that sense of palm. But what about the design? Let's then go deeper into design of the actual vibrotactile patterns and force feedback patterns. Did you use any libraries, or did you do some patterns from scratch, or how did you approach that? And then you can also talk about the frequencies that you already mentioned, actually.
Yeah, so we want to leave things as open as possible for our designers, for the creators of the VR applications. So it's not that we use on-chip libraries. We will, that's something, a design choice that we won't make, because we just want someone else. We want people to create their own waveforms for haptic feedback in a sense. And obviously you can have pre-programmed effects inside our scenes, and we have like inside our Unity SDKs and a lot of pre-programmed effects, but we really want the flexibility to either work with pre-programmed or build your own waveforms for haptic feedback. And for force feedback, it's quite easy, because we have a passive force feedback system. So we're not actively pulling at your fingers, but we only stop your fingers from moving. And there's just a variable force that you can steer with the PWM signal, like from 0 to 100, and that corresponds with the amount of current that flows into the brakes. And the more current that flows into the brakes, the fiercer the force gets, the fiercer the friction gets. And
was it like a specific decision that you are not putting like pressure instead of pulling?
It is a safety decision as well, of course, because if you just program things that are not exerting external force on your body, it's inherently more safe. And if you combine that with vibrotactile feedback, you can get quite nice effects out of it. And so therefore, also, if you like passive force feedback on its own, I won't say that is something that is very compelling as a technology. But when you combine it with vibrotactile feedback and the visual information from virtual reality, you get quite rich depth density experiences. And we did user studies, and with like 20 Newton force that we can apply, people can distinguish around 10 different types of stiffnesses of the system. So yeah,
really cool stuff. Really cool stuff. I mean, it's impressive.